Okay guys, we'll go ahead and start your second set of notes, and here we'll kind of be going over more foundations in chemistry, some atomic models, and some stuff about the periodic table. So one of the key things that we need to know about chemistry are about the elements. So surely you've heard of them by now. It was one of your discussion questions. And elements are just matter composed of one type of element. I'm highlighting that, and I suggest you do because it's a definition. It's also in your discussion questions, so it's super important that you can find that definition pretty easily in your notes. And I'm going to note here that it says one type of element. So obviously, an element that we know of is oxygen. No arguing about that. But what if we're talking about oxygen gas, which is O2? Would that still be considered an element, or would it have a different term? Well, since the definition for element is composed of one type of element, it doesn't say one singular element, it just says one type of element. O2, or oxygen gas, is also considered an element. It has a special name, and it's called a diatomic element. Di because that means two, and atomic because it has two atoms, and it's still an element. Okay, so it says here that the representative particle is an atom. When we get into the atoms, the models of atoms, we will kind of talk about the properties that they have and how those properties differ depending on the type of element that atom is. As we know, and hopefully are familiar with somewhat, they are organized on the periodic table. There are approximately 115 elements. This number is changing constantly. I think it's closer to 118 now. And it says that only 111 of them are named and accepted by the International Union of Pure and Applied Chemistry, like the governing body of chemistry, only accepts 111, or a lot fewer than the elements that we know exist or can be made. So they don't even name some of them because they're like, hey, they're not found in nature. You just made them up in a laboratory. Good for you, but we're not even going to name it. Okay. This bullet, it talks about how an element can be referring to the single atom. It could be referring to the diatomic molecule, like oxygen gas, or it could be referring to a hunk of the element. So if you have some gold and you're very rich in gold, then you still call that gold. It's the element gold, and you can hold a hunk of it in your hand. So elements obviously make up everything. So we'll talk about the most abundant elements on Earth. First, I wanted to talk about the most abundant elements in the universe, because they are very different. So in the universe, the most abundant element is hydrogen. And that makes up about 75% of everything in the universe. And then helium makes up about 25%. And then oxygen makes up, less than 1%. And then every other element that can be found is just a trace element in the universe. But since the universe is so big and so different than life here on Earth, Earth is made up of different elements than the universe is. So the elements oxygen, silicon, aluminum, iron, calcium, and sodium. And these are found in the crust. So this is like literally what the earth is made of. And since we know life on earth is a lot different than the entire universe, it makes sense that these elements also make up our earth. Now we'll move on to the top 3 elements in the human body. So hopefully, if you had me for biology or any biology class, hopefully you're a bit familiar with this. So the number 1 element is oxygen. And then in second place with 18% is carbon. And what makes up that 18%? Where can we find it in the human body? We can find it in those organic molecules like nucleic acids. And I'd suggest that you're writing this too. Nucleic acids, carbs, proteins, and lipids. Remember, those molecules of life consist of a carbon backbone that makes them organic, and so they make up a significant portion of our body. And then the other element in the top 3 is hydrogen. So if you think about it, a lot of people think that hydrogen or oxygen should be the first because we are made up of primarily water. And since water is H2O, kind of makes sense that they are in the top 3. And then the other 2, nitrogen and phosphorus, they're just in trace elements or trace percentages. So they're not even enough to really have a consistent number on how much of our body they make up. But let's look at this asterisk down here. So it says there are more hydrogen atoms than any other atom in your body. But since the mass of hydrogen is so small that it doesn't take up a lot of mass. So this is talking about just in mass. And so since hydrogen is so small, or the mass is so small, it's so light of an element, it really doesn't take up a lot in your body. Even though it's very abundant throughout your body, because there's actually double the amount because H2O. So there's almost double the amount of hydrogen than oxygen, but it's so small that it doesn't really take up a lot in your body. Okay, moving on. So let's talk about the symbols a little. We're a little familiar with some of the symbols, and or hopefully a lot familiar with most of the symbols, but you might be kind of confused because a lot of them don't make sense to us as English speakers. So we're going to talk about them for a second here. So the symbols are just the shorthand way of naming an element. So potassium is kind of a long word, and tungsten and phosphorus, and they might be hard to spell. So there's just an abbreviation for them. And symbols will always consist of 1 or 2 letters for the official names. Okay, so if there is just 1 letter, just that letter will be capitalized. For example, carbon, boron, and potassium are just symbolized by 1 single letter that is capitalized. But if there are 2 letters, then the first one is capitalized and the second one is lowercase, always. So it'll always, this is sodium, and it's N, capital N, lowercase a. That's copper, and that is lead. So let's talk about lead right here, because you might be like, and even for sodium and potassium, you might be like, well, why isn't lead Le, or why isn't sodium So? Because The world doesn't revolve and shouldn't revolve around English speakers. So a lot of the discoveries of these elements were not made in English-speaking countries in Europe. Discoveries of elements were being made all over the world in, parts of the world that don't speak English. So those countries or those scientists in those countries got to pick the names for the elements. And so that is why some of the elements don't make sense in English, because they are from a different language. And it's pretty cool. Some of the elements can't even be credited, the discovery of them can't even be credited to a single person, because some elements like gold and iron, for example, were known in ancient civilizations. So it's not like one person discovered gold and got to name it. It's just been known of for thousands and thousands of years. So let's talk about some of the weirder symbols, or non-English symbols. So Hg, hopefully we know that is mercury. And this, the Hg symbol for mercury, it derives from the Latin hydra gyrum, which I'll spell for you. Which, if we think back to our bioterms, hydra means water. So hydragyrum, it literally translates in Latin to water silver, because mercury, if you know anything about mercury, it is liquid at low temperatures, room temperatures. So if you are holding it in your hand, which you shouldn't do because it causes cancer and it's very toxic, but before they knew that, if they held it in their hands, it's a liquid. And we know that it's silver, so they literally named it like silver water. And lead's Pb symbol comes from its Latin name, which is one of my favorites, and it's plumbum. So the symbols are a good way to shorten the name of the elements, and they're a good way to communicate with other scientists, because they're not all in English. Moving on to our next page, which, if this isn't a new page for you, don't start one then. They're your notes. You can format them how you want. This is just how I had them typed up. So also along with symbols comes formulas, which, again, hopefully we are somewhat familiar with, but we will be getting way more into formulas throughout the year. But formulas are just used to indicate the numbers of atoms of each element in a compound. Okay, so the formula for water. It's a simple one that I'm sure you know of. And it's H2O. So the rules for formula are pretty simple. Each atom is represented by its symbol. So you're not going to write out hydrogen and oxygen. You're just going to write. And then the number of each type of element is indicated by a subscript to the right of the symbol. So remember, sub means below. So you write it smaller. You won't write it like a big 2, because that is very misleading. That means something completely different in chemistry. You'll always write it as a lower number. And it's to the right of the symbol. So this means that we have 2 hydrogens and how many oxygens, since there's no number written? Since there's no number written, it's just an implied 1. But we don't ever write that. And the last rule, I already talked about it. If only one atom of an element is present, no subscript is written, and it's implied that there's a 1 there. And like I said, we will talk a lot more about formulas. We will add a lot more information to formulas. There's a lot more that we haven't gotten into yet. But now I wanted to talk about the atomic models. So this is something really important in science that I want y'all to kind of understand and realize and be aware of. So basically just the word models in science. Remember, it just means that it's a way of visualizing something. In some cases, maybe we can't visualize it, so we have to have a model for it. And these models can be like 3D models, or they can be drawn, written models, things like that. For atomic models, since these particles are so small, scientists would have to experiment to determine their composition. Remember, they can't just like cut into an atom with a really like small laser, a scalpel, anything like that. To determine their composition, they had to experiment in order to find out the composition or how they were made up, what they were made up of. So the very first atomic model is pretty primitive, but keep in mind it was made in 1810. So even though 1810, you're kind of like, well, that was only like 200 years ago. A lot has been found out in those past 200 years. So our atomic model has come a long way, as we will see. So I do want you drawing these models. They are pretty important. Draw them as best you can. And I especially want you to note the years and also what that model said. So in 1810, the first model was Dalton's billiard ball model. And so it's called that because he thought atoms were solid blocks and different elements had different atomic weights. So he literally thought it was a solid ball and they just had different weights depending on which type of element it was. And there were a few discoveries in between then, but it wasn't until 1904, which is 94 years later. And so in 1904, the scientist Thomson came up with what we call the plum pudding model. And so Thomson experimented and observed that elements could be made to emit negative particles by a cathode ray tube is what he used for that. So if they could emit negative particles, he theorized that since atoms are electrically neutral, if they can emit negative particles, then that means they also must have positive material. So he thought it was just kind of a glob. The atom was a glob, and it had some negative and some positive particles. That's what it was, like an equal number of those. And that's why it was neutral. And then only a short 7 years later, in 1911, Rutherford came up with his gold foil experiment. I'm going to attempt to draw a rough kind of visual as to what he did, but basically he had a sheet of gold. That's why it's called the gold foil experiment. And he shot, and he had this, I don't know even what you call it, like a screen around it. And this is like the above view. So the gold slit, we're seeing the top of it, and we're seeing the top of the screen. And basically he shot charged particles into this gold foil. And he found that most often the particles shot around like this, but very few particles shot all the way straight back to the source of the particles. So from this, he concluded that that there must be a positively charged nucleus in order for those particles to shoot back. There has to be something pretty dense in the middle of an atom And so he also came up with the conclusion that the nucleus of an atom contains the most mass of the atom, and the rest of the atom is mainly empty space. So that's why he illustrated it this way, that in the middle is the nucleus, and then those are the electrons floating around, but mainly there's a lot of empty space. So that was kind of a revolutionary experiment in the atomic models, because it did come a long way. But then in 1913, Bohr came up with the planetary model. So going off of what Rutherford said, that there's an atom, a dense positive atom in the middle, he kept that idea. But then he thought that the electrons, instead of jumping around randomly like Rutherford thought, he said they have a fixed circular orbit around the nucleus, kind of like the planets circle the sun. The electrons circle the nucleus, is what he thought. And he also hypothesized that the outer orbits can hold more electrons. Okay, and then it wasn't until 1932 that Chadwick adapted Bohr's model just a tad, because he identified that neutrons were the particles in the nucleus with a similar mass to that of a proton, but they had no charge. So remember, neutrons are neutral. We draw that with a little, like a degree symbol basically. They're neutral, which is why the nucleus is dense, because they're made of neutrons and protons, but they're still considered positive. As he said up here, they're positive because they have protons and this neutral particle, so they have an overall positive charge. And today, many advancements were made, but we didn't really change it until the model that we have today, and we adopted a few decades ago, and that is the electron cloud or quantum model, and it's the most modern model of the atom that we go by. So today we know that electrons occupy regions of space that we call orbitals around the nucleus. So in this model here, they've kind of drawn it, and it kind of looks like a flower, but just know that they kind of just circle back and forth, like they ebb and flow, or it's like a wave where they don't follow a circular orbit. Depending on which level they're in, they have a different wave pattern or path to follow. And this is determined by their energies, and like I said, they're seen as waves. So not circular, they kind of ebb and flow throughout the atom, sometimes being more close to the nucleus, sometimes being further away from the nucleus. And I liked this illustration for the atomic model because even though the atomic model that we base our ideas off of now, it is the most recent, and we think it's, the most correct. It's the most correct model we've ever had, but science is constantly changing. Technologies are constantly changing, so there's nothing to say that scientists won't adapt that model any further. For now, it's good and it's what we go off of, but as scientists find new information, we could always come up with a new model. So for the modern atomic theory, we know that the atom is made up of 3 particles: proton, which we abbreviate this way, neutron, which is we abbreviate that way, and electron, which we abbreviate that way. If you look at their actual mass and relative mass, you can see that the electrons are actually and relatively lighter than the proton and the neutron, which, if you're paying attention, the proton and the neutron have the same mass. And the charge, as indicated by their symbols or their abbreviations. The proton is positive, which is easy to remember because they both start with P's. The neutron is a neutral. So a lot of times people think, oh, neutron is negative because it starts with an M. No, the neutron is neutral, which they sound alike. And then the electron is the negative particle. And as we know from the models that we just looked at, the location of the protons and the neutrons are in the nucleus, and then the electrons are orbiting around the nucleus. And I think this is a pretty cool fact in a way to visualize really how small these particles are. So if an atom were the size of the Astrodome football stadium, so really you can think of any football stadium because they're all about similar size, like a pro football stadium. They are huge. So if the entire atom, which is the smallest particle that we know of, was the size of the football stadium, the nucleus would be the size of a fly at the center of it. So think about that. If the nucleus has most of the mass of the atom and it's just a fly at the center of the Astrodome, that leaves a ton of empty space. And relatively, the nucleus is incredibly small compared to the atom, which is the smallest particle that retains its properties. But inside of the atom is something even smaller, which is the nucleus. So that's just a little fun fact for you. So we have talked about the periodic table somewhat, like the history of it, and kind of the genius behind it. Because, like they talked about in the videos, and we talked about in class, based off of the math and what they knew of the trends in the periodic table, they were able to predict some of the elements that hadn't even been discovered yet. But remember, like, he left little spaces in the periodic table because he was like, no, I know that I'm confident in my idea and this is right. This is how they should be ordered. So he knew that there would eventually be one found that fit in that place. So pretty impressive. So there are trends. They are arranged in certain ways. So the elements are arranged in order of increasing atomic mass. So the number beneath the symbol, typically a decimal number, is the atomic mass. And then we talk about the periods, which are the horizontal rows, the rows going that way. And then the groups or the families, typically I'll refer to them as groups, and a lot of people will, but they are also known as families because they have similar properties, so they're like called families. Those are the vertical columns. They go up and down. So I'd recommend that you have your handy dandy periodic table out in front of you so you can kind of like be looking and following along. So in groups, the elements of a group have similar chemical properties. So they have the same valence number, which means the same number of electrons in the outer energy level. So remember, the electrons are kind of arranged in levels, floating around in the nucleus or in the atom outside of the nucleus, and this is in the outer energy level. So, for example, if you're looking at the periodic table, group 2, which is just the second group from the left. So beryllium, magnesium, calcium, strontium, barium, and radium, they're in the same group, they're in the same family. They will all have the same number of valence electrons. And pretty soon when we start talking about it, you'll be able to figure out how many valence electrons they have based on their position on the periodic table. So the periodic table is just a wealth of information that we are going to spend some time like marking up and identifying. So the metals, those are found on the left and the center. So if you have your periodic table in front of you, starting at group 1, period 2, you should be at lithium. That entire group below lithium, all of group 2, groups 3, 4, all the way through 12 are considered metals, also including other metals that we will talk about, but generally like the left side and the middle is the metals in general. They do have, or another property of them, they are good conductors of heat and electricity, which I'm sure you knew, but maybe like didn't put together. But typically, any conductor of heat or electricity is going to be metal. Metal, which is typically why like your pans are made out of metal, because they conduct heat really well to heat up your food. That's why electrical wires are also made out of types of metal, because they can conduct electricity across the land. They do have very diverse properties, which are listed on page 18 of your books, which we will look at thoroughly when we go into marking up the periodic table. So don't worry about those properties just yet, because we will find out about them. And then the last property of metals is that they tend to form positive ions, also called cations, which means that they lose electrons. And we will go over that in more detail. Maybe I'd make like a little star for that one, meaning like, hey, we learned about it, but we're going to go over it more later when we start talking about ions. And then the next type of elements on the periodic table are nonmetals, and those are found on the right. And those consist of halogens, noble gases, and other nonmetals that we will mark specifically when we mark on our periodic tables. But nonmetals are categorized by being poor conductors of heat and electricity, because if metals are good, then nonmetals kind of have to not be good at it. And opposite of metals, nonmetals tend to form negative ions or anions, which means that they gain electrons. So we're going to star that one too. And then a third type are the metalloids. So these are the ones I kind of mentioned up here with metals, but they are elements with a side touching the separation line, which we'll talk about when we mark up the periodic table. And these metalloids, they have some metallic properties and some non-metallic properties. So the typical information provided on the periodic table are things like name, symbol, atomic number, and average atomic mass. So the atomic number is typically on the top, and that is a whole number and how they are ordered. And then the average atomic mass is the number below the symbol or the name, and that's typically the larger decimal number. So the atomic number, which is called Z, the atomic number is the number of protons in the nucleus. Okay, so this is super important. So if you're looking at your handy-dandy periodic table, find aluminum in group 13. Its atomic number is 13. So that means that it must have 13 protons in the nucleus. And then down here, this sub-bullet says for an atom that's electrically neutral, the number of protons is equal to the number of electrons. Because remember, as a whole, the atom is neutral. So that means if there are 13 positively charged particles, to make it neutral, there must be 13 negatively charged particles. So just by looking at the box for aluminum, you can tell that it has 13 protons and 13 electrons. Now talking about the average atomic mass. That's the decimal number, and it's the total weight of particles in the nucleus. It's measured in AMUs, so it's not measured in like grams or anything like that. It's measured in atomic mass units. So because the mass of them are so different, they couldn't use a standard unit of measurement that already existed. They had to come up with their own for atoms. So it means that one AMU is defined as 1/12 of the mass of a carbon-12 atom. That's just a little fun fact for you. And when you're using for calculations, you're just going to round them to one digit after the decimal. Depending on what number it is, they could give you quite a few decimals after, but we're just going to use 1. Okay, so that sums up the cursory information about the periodic table and the atomic theory. And like I said, we are going to talk about all of these things more. We're going to get lots of practice with them. This is just kind of the introductory, so you kind of know what to expect. Okay?